The network fabric. The network fabric refers to the interconnected infrastructure that enables communication and data transfer across a network. It encompasses hardware devices, software, protocols, and cabling, working together to ensure seamless connectivity. This intricate web supports the flow of information, maintaining efficiency and security. Essential for modern digital operations, it forms the backbone of data centers and enterprise networks.
Overview and standards. The network fabric is a crucial component of the IoT product, responsible for transporting both internal data from the hardware-defined product and external data from other systems to the software-defined product. It comprises the operational technology, OT, network, which operates within the product, and the information technology, IT, network, which transmits data to the cloud. Additionally, it includes the backhaul, uplink, the Internet, and the product cloud, a dedicated private computing resource for the product. Beyond mere connectivity, the network fabric functions as a distributed computing platform, offering both computing and storage capabilities. Communication within the network fabric is facilitated by protocols, equivalent to standards or layers, which enable different parts of the network to interact. In the OT network, these protocols have evolved independently to suit specific purposes, starting from simple screen communications to machine-to-machine interactions, and eventually within local area networks. There are three primary IoT protocols: the media layer, which organizes information for radio transmission; the networking layer, which manages data transport within the OT or IT network; and the application layer, which provides contextual data along with the data payload for applications. Additionally, there is a meta layer, not yet standardized, that constrains the vocabulary used in the application layer. IoT protocols can be visualized as nested Russian dolls. The innermost layer is the payload from the sensor, wrapped by the application protocol that adds contextual information. This is encased by the network protocol, which guides data movement along the network path. Finally, the media protocol envelops the network protocol to enable radio-based connectivity. The network fabric acts as the plumbing that interconnects various parts of the IoT product. While essential, it's not an area where companies should focus their intellectual property development. OT, IT, and fog networks. The fog layer comprises both OT, operational technology, and IT, information technology, networks. Its primary role is to facilitate the transfer of data from sensors to the backhaul that connects to the Internet. OT networks are tailored for specific operational functions, supporting various industries by connecting sensors and actuators. These networks have developed individually and are often proprietary, typically embedded within the product, which can range from discrete items to systems or environments. They can form personal, local, or wide area networks and generally consist of gateways, leading to the term Internet of Gateways. OT networks utilize numerous proprietary protocols designed for specific purposes like automation, industrial control, and building management. The IT network, the second half of the fog, connects to the OT network via radios such as Bluetooth, Wi-Fi, cellular, or LPWA, with wireless connections being common, though Ethernet is also used. The IT network's function is to transfer data from the receiving radio to the Internet. For example, in an IoT dryer, data from sensors travels through the OT network and is then sent wirelessly via Wi-Fi, becoming part of the IT network within the home before reaching the Internet through a router and fiber uplink. IT network hardware includes routers, switches, and firewalls, standardized on the Internet Protocol, IP, unlike the diverse OT protocols. The gateway, which translates between OT and IT networks, poses a security risk as a common attack target. Over time, the fog layer is expected to unify under the IP protocol, simplifying and securing the network by replacing OT network protocols. The trend towards edge computing involves moving computation closer to the data source, starting with gateway computing in the OT network and progressing to mist computing on embedded systems. Ultimately, this integration will extend IP protocols to the end nodes, phasing out proprietary OT protocols. IoT Product Cloud. The product cloud can be viewed as a powerful computing extension specifically designed for IoT products. This private cloud enhances the computing, memory, and storage capabilities of these products. Unlike the traditional IT cloud, the IoT product cloud employs distinct technologies and business models. Technologically, it must accommodate various application protocols, diverse analytics tools, and different development environments. It also needs to support APIs for various data services that are not typically utilized in IT networks. On the business side, the IT cloud model, which caters to a smaller number of users with high bandwidth usage, does not fit the IoT scenario, where numerous users consume less bandwidth individually. Thus, the traditional IT business model cannot be applied to IoT architecture. Imagine the immense computing power available for any product. An IoT dryer, for instance, could leverage an entire data center's worth of servers to deliver exceptional functionality when required. IoT platform. The IoT platform packages and commercializes much of the network infrastructure needed by IoT products. Essentially, an IoT platform acts as middleware, incorporating the IoT product cloud, the IT network, and sometimes parts of the OT network. Occasionally, it also includes a development environment. There are three main types of IoT platforms. First is the Application Enablement Platform, AEP, which offers a comprehensive platform for manufacturers to develop applications within the networking context. The second type is the Provisioning Platform, with roots in M2M and telematics, primarily used to provision SIM cards for cellular connections. The third type is the Connectivity Platform, a subset of the AEP, which establishes connections between embedded system software modules and the Internet, commonly used in connected products. When using an IoT platform, it's important to consider the risk of dependency on third-party infrastructure. Developing applications in a modular way allows for easier migration to different platforms. There are two main IoT platform architectures: publish-subscribe and client-server. The publish-subscribe architecture, which uses messaging, is generally easier to implement but has less predictable data delivery times. The client-server architecture, while more complex to implement, is suitable for real-time applications. Most companies should consider buying or renting an IoT platform, as developing this middleware in-house, while functionally significant, is not strategically essential.
Thanks for joining our video. Would you be interested to know more? Please contact us to www.icertglobal.com or email to info@icertglobal.org.